Assalamu alaikum. Welcome to Digital Communication course. Today we are going to continue our discussion regarding the optimum receiver structure design, and inshallah with the help of an example we would see how the receiver works and takes decisions in the favor of a signal class that was sent. We have seen few topics before we started the optimum receiver structure design. The topics include match filters, correlators, and vector signal space, and the determination of the basis functions out of this GSO process. We've already seen these topics in details and with examples as well. In the last lecture, we have derived the optimum receiver structure design, and we have seen the mathematics behind it. We have concluded few important results out of it. I will review those important points before we move on with this topic and finally do some examples related to it. In the next lecture, we would be covering probability of error analysis in detail with the help of examples to complete this chapter number 3. So let's see what we have done in the last lecture. Right, so we consider the simple communication model in which we have a very nice channel, that is, we don't have any interference from any other sources, or there are no other people communicating over that channel. We only have noise present in our communication channel, and it gets superimposed onto our transmitted signal like this. Okay. We have also seen the review of these important probability definitions. They are involved in the course of derivation throughout the topic. We started off with this very basic rule, that is the maximum a posteriori rule or criteria. We have seen how we can take decision in the favor of either hypothesis H0 or H1 in the case when we have only two signal classes to deal with. We compare these a posteriori probabilities and take the decision in favor of one of the hypotheses depending upon whether one of the probability is greater than the other one or not. We extend our discussion to capital M signal classes and generalize this rule for M signal classes in this slide. We also have seen that we can represent our signals in terms of basis functions using GSO process, and the same maximization rule then turn into this form, which is nothing but the maximization of the product of marginal PDFs. In the next step, we substituted these probabilities in this maximization rule and solved and simplified this maximization rule in the next few steps. It turned out that the maximization rule becomes the minimization rule if it is expressed in this form, in which R and Sk are the two vectors, and this representation is nothing but taking the Euclidean distance between these two vectors. We conclude an important result at this point, and which is expressed here, that the map detector reduces itself to maximum likelihood detector for equally likely signals. That is, when we assume that all signals are equally likely, then this probability term will appear to be a constant term, and it will not influence the maximization or minimization rule. So we remove all those terms that do not influence the maximization or minimization rule, and we are left with this term only, which is nothing but the calculation of Euclidean distance between R and all possible signal vectors Sk, where k varies from 1 till capital M. And we call it minimum distance detector because we are going to take decision in favor of the signal class k that is going to give the minimum Euclidean distance out of all the possible distances. Right? This was explained in the last lecture in detail. We also expanded this term again here and tried to have another look at it in a different aspect. It turned out that we have three terms as a result in the minimization rule, in which one of the term was nothing but the energy of the signal class k, and this term, the third term, is nothing but the probabilities of the signal class Sk. And the second term here is very important term. This is something which we have discussed last time, and the signal version of it is nothing but the correlation between signal R and the possible signal Sk. We will continue our discussion from this point onwards in the coming slides. If we assume equally likely and equal energy signals, such as assumed here, so that the two terms, this one and this one term, these two terms will become constant and they will not influence the maximization rule and will be taken out. The only term left will be this term here, which I have shortly talked about. This is nothing but the correlation between the received signal R and the signal class Sk of t. If you express this term in terms of a block diagram, if you realize the block diagram out of this mathematical equation, you see you have multiplication of received signal R with all the signal types 1 till capital M, and then integration of it. So here we have the received signal R being received. It will go in all these branches there. All these multipliers are unique multipliers indicating S1 of t till Sm of t. And here you are taking the integral of each of these multiplier products. Here you are taking the sample t is equal to capital Ts and coming up with the test statistics at each of these branches there. And since we are taking the decision in favor of the branch that gives the maximum result, so here you apply the maximization rule. You select the branch that results in the maximum test statistic out of this integral and sample at t is equal to capital Ts, right? So if you realize this mathematical equation, it will spit out this block diagram as a result. You can also have the match filter implementation of the same when you replace these correlator blocks with the filter having some impulse response, and we have also seen that topic a couple of lectures ago, that how the match filter and correlator detector are basically the same thing. It's the way you look at these two things differently, but they are actually the same. Here is the match filter implementation of the same, and this correlator representation can be mathematically expressed like that very easily using the convolution operator, but you have to flip and time shift the signal type Sk with Ts amount, right? In this we have already seen a couple of lectures ago how these two are equivalent at t is equivalent to capital Ts. So if you implement This equation now, all you need is to realize these filter blocks. How many such filter blocks? Capital M such filter blocks will be there. Since we haven't represented these signal classes in terms of basis functions as of yet, so we would have to use capital M signal blocks there. After the received signal has passed through all of these branches, it will be sampled at t is equal to capital Ts, and again the maximization rule will apply here, and you will take the decision in favor of the signal class that will result the maximum result out of these branches, right? So M correlators or match filter can be replaced by N match filters, provided you have computed the basis functions and represented your signals in terms of the basis functions. And yes, we can do that, and since capital N is always less than or equivalent to capital M, so the choice is obvious. We would like to go for the basis function implementation of the same, since this reduces the number of match filters required at the receiver end. Therefore, we would like to go for this. And in the next slide, we would see how we can have the basis function implementation of the same map decision rule. Right? Alright, so in this first step, we have replaced R of t and Sk of t in terms of their basis function representation, respectively. Let me give you a reference for that. If you go back few slides there, if you see here, Sk of t is represented in terms of the basis functions along with the contributions, right? So it's the sum of the contributions of all the basis functions used in the process. Here we have capital N basis functions, and the types of signals are capital M. So K varies from 1 till capital M, and I varies from 1 till capital N. Ski is the kth signal's contribution using the ith basis function, and I varies from 1 till capital N. So we can represent Sk of t in terms of the sum of the contributions of all the basis functions, right? And likewise, we can do it for the received signal R of t, and we can express it using the basis functions. So let's go back to this diagram. Here we have substituted the basis function representation of the two signals R of t and Sk of t respectively, right? Alright, so now let's see what do we have here in this second step. We can see an integral moved a little bit inside this equation, and we would like to explicitly see and realize the block diagram out of these terms. Okay, this is nothing but the received signal being multiplied with all the basis functions phi i's of t and being integrated. If you see here, if you realize this in terms of a block diagram here, right? So if you realize this term in terms of a block diagram, it's nothing but the received signal being multiplied with all the basis functions ranging from 1 till capital N, and then taking the integral of their products, right? Let's see what happens next. If you move this integral a little bit further inside, you will see the product of the basis functions there and integrated over 0 till capital Ts. Now we have seen one of the very important properties that is associated with the basis functions, that if these two basis functions are same, their integral will give you 1. And if these two basis functions are different, they would be orthonormal to each other and the answer will be 0, right? So as we have these two summations being applied on these basis functions respectively, these summations vary from 1 till capital N, and but with different indices I and J respectively. So whenever J is equivalent to I, this product and integral will give you unity. Otherwise it will give you 0. So this product and integral will only hold for all values of J when it is equivalent to I, right? So this J varies from 1 till capital N, and whenever it is equivalent to I, it will give you 1 as a result, right? So we can reduce this equation in this form, and we can replace R of J with R of I, because whenever J is equivalent to I, this equation will give you 1, otherwise it will give you 0. So 0 multiplied by the whole thing will give you 0, right? So in order for this equation to hold true and give you some finite value other than 0, J has to be equivalent to I. That's why the index here is replaced with I in this step, right? So when you substitute the signals in terms of basis functions, the same maximization rule becomes equivalent to the product of these contributions Ski and Ri summed over all the possible number of basis functions from 1 till capital N, right? So whenever J is equivalent to I, this will give you 1, right? Whenever J is equivalent to I, and it will give you 0 otherwise, right? So in order to get a non-zero value, J has to be equivalent to I, and here you can see previously it was R subscript J, but now it is R subscript I. So we have replaced J with equivalent to I, and for other values of J, this equation will give you 0, right? So this summation is mentioned here in this block. You have to compute this, and in the end you have to go for the signal class that will give you the maximum result of out of all these possible branches, right? So that's how you realize the block diagram when you represent the signal in terms of the basis functions. You can have the match filter of the same map rule. Here we have used the match filters instead of the correlators in the previous slide. You can see the correlators are being replaced with the match filters. Each match filter has an impulse response that is matched with one of the possible basis functions type. Phi 1 of ts minus t, phi 2 of ts minus t, and so on till phi n of ts minus t. Right, the same block diagram, only we have replaced the correlators with the match filter, right? Now let's see how we can further understand our concept using an example. This is a very simple example in which we consider only 4 signal types, capital M is equivalent to 4, that could have been sent from the transmitter end. Assume we have 2 basis functions computed out of the GSO process, that is capital N is equivalent to 2, and we have represented the 4 possible signal types using the 2 basis functions in the constellation diagram like this, right? We also assume that there is no noise present. We only want to see the functioning of the map detector. So we assume a hypothetical scenario in which there is no noise present. That is, whatever we are going to send from the transmitter end we will receive it as it is at the receiver end, right? But receiver still has to go through all the branches and compute all those integrals and results to compute the decision in favor of the signal type, right? So let's assume that there is no noise present in this particular example. And what we have to do is to design the map detector and show how it takes the decision, assuming S1 of t was sent, right? So let's assume that S1 of t was sent from the transmitter end. Have a look at this constellation diagram. We have placed all the signal points there in the constellation diagram, all 4 points, S1, S4, S3 and S2, using the two basis functions phi1 of t and phi2 of t. It's not visible here. Phi2 of t is there on the y-axis, right? So we have two-dimensional constellation diagram, and all 4 signals are assumed to be equally likely and equal energy. That is, the norms of the energy is under root E. All of them are equal energy signals. All right. And we have also assumed that there is no noise present in this particular example scenario, and one of the signal type S1 of t was sent from the transmitted end. The representation of that signal using the basis function is highlighted here. S1 of t is contribution of the first basis function, which is 0.707 times under root E, plus contribution of the second basis function, which is again 0.707 times under root E. This is given, when these points are given in this example, right? So that's how you represent the signal in terms of the basis function. All the signals can be equally represented like that. All right. So we assume that signal class S1 of t was sent from the transmitter end. Now let's see how the optimum receiver finds out and takes the decision in favor of the signal class S1 of t. We have two basis functions, right? So we have two correlator blocks, one with phi1 of t, the other one with phi2 of t. We have two branches, right? Remember, we have talked about it before, that the number of branches that we are going to have at the receiver end depends on the number of basis functions computed out of the GSO process. So we have two basis functions, that's why we only have two branches, and our signal is completely represented with these two basis functions, right? So we already know this. So we are going to have two branches here at the receiver end, one for phi1 of t and the other one for phi2 of t, right? Next we have the integral block, right? Computing some result here. I'll show you how did we compute these results there, and thereafter we have to compute the summation. Remember this block diagram? We have to compute the summation as well, right? And then we will have some results in these branches, and the last block is going to take the decision in favor of one of the classes depending upon which branch will result in the maximum result. All right. Right, next let's see how we can compute various values at each stage of this block diagram, and for all of the values of k ranging from 1 to capital M equivalent to 4, and for all values of I ranging from 1 to capital N equivalent to 2. Let's see this value here. How did we compute these two values in first stage? The received signal is received here and is placed in both of these two branches. It will get multiplied with the basis function phi1 of t. It's like saying that you are multiplying this received signal S1 of t with phi1 of t, and here in the second branch you are multiplying the same signal R of t with phi2 of t, and then integrating the result. You see, when phi1 of t is getting multiplied with phi1 of t and integrate it over the symbol period 0 till ts, it will give you unity answer, that is 1 times 0.707 under root e. Whereas in the other term, the integral will give you 0. Why? Because phi1 of t is getting multiplied with another basis function phi2 of t integrated over the time period 0 to ts. So whenever you have two different functions, two different basis functions being integrated over the period, it will give you 0. So one portion of this multiplication and integral will give you 0.707 times under root es, and the other portion will give you 0. So in the upper branch, you will have 0.707 times under root e coming out as a result. And again, for the lower branch, the first term will give you the result 0, and the second term will give you the result 0.707 times under root e, which is placed here. Now these are your two values, r1 and r2 respectively, as mentioned in this diagram there. You can see r1, r2 till rn. Since we have two basis functions, so we only have two branches, and therefore the two respective results r1 and r2 as a result of this multiplication and integral operation, right? So in this step we have computed r1 and r2, and which was very simple to understand. That's why I have skipped writing those steps. Here I expand further this summation for all values of k, starting from k equivalent to 1 till 4. So if you see this summation here, when you substitute k equivalent to 1, you will end up expanding like this. r1, which is 0.707 times under root e, being multiplied with s1 1 plus r2 being multiplied with s1 2, right? So if you expand this summation, you will get two terms, and you write it like that. Sum them together, you end up getting under root e as a result, right? The same process is repeated for other values of k. In the next slide, you can see for k equivalent to 2, you expand the summation like this, and you end up getting 0. If you expand them and substitute the values of r1 and s21 and r2 and s22, you end up getting 0. Let me tell you the values. For example, this is s2, and s21 is nothing but the second signal contribution using the basis function 1, which is what? Which is 0.707 times under root e. And if I ask you to calculate s22, represent s22 out of this constellation diagram, it will be nothing but the second signal represented using the second basis function, which is along the y-axis, and the value for it is minus 0.707 times under root e. It is substituted here. You can see here s22 is substituted as negative 0.707 times under root e. Now this summation will give you 0, right? So you repeat the steps for other values of k, and you end up getting these results. You see, you got under root e here when k was equivalent to 1, 0 when k was equivalent to 2, 0 when k was equivalent to 3, and finally minus under root e when k was equivalent to 4, right? So you got 4 different results for 4 different classes of signals ranging from 1 till 4, right? So 4 different results for 4 different branches. Under root e on top, 0, 0, and minus under root e in the bottom, right? So what's the next block? If you see, the next block is going to compare all these results that have come out of this summation. 4 results have come out, right, in our example. So the next block is going to select the signal class that will give you the largest result, right? So the largest result in our example is there in the first branch, which is under root e, the maximum result among the 4 results, right? If you compare the 4 results, under root e is the highest among all the other results, right? So which one is max? That is the branch with index k is equivalent to 1. That is, the first branch has the maximum result, right, amongst the all results. So the receiver is going to take the decision in favor of the signal class that resulted this maximum result, which is nothing but the signal class S1 of t, right, which is corresponding to k is equivalent to 1 index, right? So that's how the maximum a posteriori block computes and takes the decisions in favor of the best possible signal class that was sent from the transmitter n, right? So even if you assume the noise to be present, this receiver may take correct decisions as long as the noise is below a certain threshold value. You can have another example in which you may include the noise, and you may assume that the received signal is not exactly one of the signal type that was sent, but slightly offset from what was sent. That is, if you assume the noise is present, you may not receive S1 or S2 or S3 or S4 as it is, like they are mentioned here in the constellation diagram. They might be offset by some amount. Let's say S1 be placed there because of the noise present in the signal, right? But even then you can take correct decisions, and this receiver would be able to find out which signal class was sent, unless there is so much noise and the noise has moved the signal far away from the actual constellation point, right? So in that case you are going to make errors, and we will talk about the errors in the coming lectures, how this receiver can have actually errors in its decisions, right? All right, I hope you understand the example. Now let's see how we can have slight modification of the map detector that incorporates different scenarios, such as the one here mentioned in the slide. We have equally likely signals, however they have unequal energies, right? So let's see how the block diagram incorporates the unequal energy scenario. It will be a very slight modification. The core block diagram will remain same, however the unequal energy part shall be added into the block diagram as mentioned in this slide. You need to recall the equation while we were deriving the map detector. We came to this point in which we were calculating the Euclidean distance between the vector r and sk, and if you expand these equations you end up getting these three terms, right? And like I said, we have unequal energy scenario, so therefore we can't ignore this energy term anymore. Earlier it was assumed to be constant since we had equal energy scenario, and the constant do not influence the maximization rule. That's why we moved it out of the equation, right? But now we have unequal energy scenario, that's why we can't move it out, and we have to include it in our maximization rule. And as a result we end up getting the correlator term and the this additional term, which corresponds to the unequal energy accommodation into the block diagram. So this is nothing but the same correlator implementation or match filter implementation, and on top of it we have to subtract few terms. That is, we have to subtract the energy of each signal once we have calculated the correlator output, right? So we have accommodated the unequal energy part by including these terms on each of the branch here before we take the decision in favor of the largest branch, right? Similarly, we can have the match filter implementation of the same. We replace the correlator with the match filters, and the rest is the same. And we can also have basis function implementation, basis function with correlators and basis function with match filter, and the rest remains the same. Okay, Similarly, we can have a very generalized block diagram of the optimum detector using correlator that incorporates unequally likely scenario of the signals. Unequally likely means the probabilities of the signals are not the same. If they're not the same, we can't ignore this term as well, right? And we also assume that the signals are having different energies. Therefore, we can't ignore this term as well. So both of these two terms shall be included in the maximization rule and can't be ignored anymore, right? So let's denote P of k as one of the terms there, and E as k over 2 will be used as it is here in this maximization rule. And when we realize the block diagram, we have to include two separate additions in each of the branch, right? One for the unequal energy scenario and one for the unequally likely probabilities, right? So you can see here the main block diagram, the core block diagram remains the same, and we have included the two terms that result out of this equation, right? Before you take the final decision. And vice versa, we can have match filter implementation of the same with the two terms mentioned here. By the way, the two terms are combined in one variable ak in the slide, and edit here using one simple adder, which is nothing but the addition of the two terms. Now, depending upon the scenario, whether the two signals are equally likely or equal energy, this AK will vary. For example, if I assume that the signals are equally likely and equal energy, this AK will be 0, and you don't need to add anything here, right? And if the signals are unequal energy then and equally likely, then this term will be taken out of the rule, but this will be present here, and the AK will be nothing but the energies there, right? So this is the slight modification of the main block diagram, nothing special about it. And we generalize these results like that. You will see this kind of a block diagram. You will encounter these block diagrams in many different books, and whenever you are going to talk about the optimum detector based on maximum a posteriori criteria, you will encounter these block diagrams, the generalized block diagrams, right? So in summary, we have digital modulation schemes that are represented by finite number of waveforms, that is ranging from S1 of t till capital Sm of t. And we can also represent these signals in terms of finite number of basis functions, where the number of basis functions are always less than or equivalent to capital M. Of course, when they are less than capital M, then we can reduce the complexity of the receiver design. But when they are equivalent to capital M, we are unfortunate in that scenario, and we won't be able to reduce the number of branches required at the receiver end for the match filters, right? So in short, the optimum receiver requires the parallel bank of match filters or correlator receivers that are matched to Sk of t. And if you use the basis functions as their representation, then you require the parallel bank of match filters or correlators that would be matching to the basis functions, right? And it's best to use the basis functions for the representation, because it reduces the number of branches required at the receiver end, right? So that's the summary of the map detector, and we have gone through it using an example, and in the same way you are going to design it in the labs. When you are going to realize the receiver unit, you are going to have to refer back to these equations that we have talked about, and especially this example, this simple example to start with. All right. So if you have questions, you can ask me in the interactive session, and after this lecture is uploaded, you can have the interactive session in the following week. Next, I would be talking about few more related topics that is mentioned here in the slide. You can see we can have another criteria on the basis of which we can take decisions in favor of either of the classes. For example, you have two signal classes S1 and S2. Then both of them are represented on the constellation diagram, right? They can easily be represented there. And you can easily divide the constellation diagram in two regions, that is region S1 and region S2. And if the received signal in the presence of noise falls under this region S1, it will be classified as if the signal class S1 was sent. And if the region, if it falls in the region S2, here in this region, it will be taken as if the signal class S2 was sent, right? So there lies some threshold boundary that determines the region, right? And how do you find out that threshold boundary? You connect the two signal classes together and compute the perpendicular or the bisector, draw the bisector on that particular line, and as a result it will bisect the regions, right? You will have these two regions, one region here and the other region there, right? And whenever the signal class falls in either of these regions, you will take the decision in the favor of that particular signal class to which that region belongs, right? So this is another way of going about, and it involves the calculation of the thresholds, right? And there's this slide in which I have calculated the optimum threshold, this one there. And this is something not that difficult. It looks difficult, but it's not that difficult, let me tell you. I will derive this result in the next class for you, and from thereafter, once we have done this topic, we will move on to the error analysis, probability of error analysis, which is also very interesting. We will see how we can compute the probability of error given the AWGN noise present in the communication channel. All right. Thank you very much.